Hello. There we go. Always check to see if your mic's on. All right. Um, so yeah, today will probably be the last, I guess, episode of Lit Review because I have to present later today. So, oh, okay. Okay. So what I want to do first. So here's the paper. All right. Um, First, I just want to read through the paper completely. I think. Where's my PowerPoint? There we go. And then maybe towards the end, I'll like go through the entire presentation. Okay, so studies explores looking driven, which is known as open and closed listing string-free energy simulations. We determine the free energy profile for both enzyme opening and ligand release and compare them with profiles from the APO enzyme. Results reveal a three-step ligand release process, which initiates the opening. Okay, the lid, AMP. Alright, that's all fine. So let's skip the background. Um, I think we've already read this last stream. It's just going over like previous studies. We employ it. Okay, so this is what I'm interested in. String method and collective variables to investigate the mechanism of AK's conformation. This method has been successfully used by our group to study this enzyme and other enzymes, providing valuable insights to the mechanism. By comparing the free energy profiles determined for the enzyme in various states, including the reactant products as well as APONET, we showed the involvement of both the induced and conformational selection mechanisms. Specifically, the binding of ATP's phosphoryl groups to the closure of ATP. This is equivalently the ATP that undergoes conformational selection. This mechanism understanding is consistent with our recent studies. Cool. All right, so this would probably be the next figure I show. What is A? SMC. Okay. Interesting. Yeah, I'll show that next. Uh, put it right here. Slide. Place it right there. There we go. All right. All right. Materials and methods. The reactant product state systems were prepared using atomic coordinates for wild type and closed conformation, where the reactant state system was prepared with ATP. Okay. Um, so this is strange to me right here. As described in our previous studies, the removal of protons led to significant distortions in the orientation of the molecules. So do they have a protonated ATP, AMP? The box is ginormous. Um, Okay. 3 MSM trajectories with different closing times were selected, each representing the pathways with fast, middle, slow closing rates. For each MSM pathway, a total of 40 coordinate sets were selected to represent the initial opening and closing rate. So they got these coordinates from this paper, which I think I already looked at, and it's not something that they provide in the paper, unfortunately. So they must have reached out and asked them, maybe. Okay. They were equilibrated during the MD proteins were Charm 36 with CMAP correction. Tip 3P model was used. Now I'm wondering if they're mixing force view. Like, is tip 3P compatible with Charm? Um, okay. Cool. All energy minimizations performed using Charm, or yeah, they misspelled that, but unless, yeah, they misspelled that. The MD simulation was carried out using the product relay. Shake was applied to constrain all bonds involving the hydrogen atoms. Okay. SV, yeah, there we go. That's what I'm interested in. To generate the initial pathway for 2 microsecond MD were performed for the product state at that the temperature and pressure of the simulated system were controlled cyclically. During this MD, the enzyme opened around 1 microsecond while its ligands remained interacting with the enzyme. To complete the ligand release and to generate paths for the ligand release, and then generally pulled away from the enzyme in a manner similar to steeled MD with distance restraints from their centers of masses from their respective binding pockets over 6 picoseconds. This was followed by the equation. The trajectory thus obtained was used for the initial. The reactant state, the same length of MD did not open. Thus, the trajectory obtained in PS was adopted. Starting from the initial pathway generated features. Okay, so they're basically just doing standard steered MD. They're like pulling away the things. I thought they did something more um, different. Starting from the initial pathways generated for each system was performed in an iterative manner. Namely, each iteration the system was first simulated, during which the SM image was harmonically restrained with force constants. Okay, I don't really understand that. For the reactant state, the same length did not open the enzyme as discussed in a recent study. Thus, the trajectory of Jade in product state was obtained with modification, followed by 1 nanosecond. So I guess they're protonating the ligands there. Starting from the initial pathways generated for each system, this SMCV path was performed in an iterative manner. Namely, in each iterative system was simulated for 4 picoseconds, during which each SM image was harmonically restrained, the force constant, to each CV. was then evolved, followed by the reprimation. Okay. Okay, I think I see what they're doing. Basically, they did like regular steered, and they just got the ligand to come out, and then they're looking at those frames, and they are running an MD while restraining the um, positions along the CV, like the collective variable path. I think there's something like that. Followed by reparameterization of CV positions of equal distance between neighboring images. Okay. So I guess they're trying to find like, I don't know, like a equidistant series of steps that lead to um, binding or unbinding, kind of. Was it involved? The CVs were defined to describe the opening. Okay, so let's figure S1. Once the path was performed, additional for each SM image without updating the CV positions to determine the potential mean force. Okay, yeah, this is kind of complicated. Okay. Alchemical transformation simulation of catalytic reaction. They're doing alchemy. The alchemical free energy simulation method was utilized to simulate phosphorus transfer. Ooh, that's cool. Oh, did they just replace the things then? Is that what they mean by that? Starting from the reactant state, this system was progressively mutated to the product state. There's 17 discrete steps. At each, what is that, gamma? I always forget these. No, it's lambda. At each lambda value, the system was simulated, and the lambda value was updated. Okay. So there's 17 discrete steps. Wow. System was simulated for 1 nanosecond. Five times, total of 10 nanosecond MD simulations at each. Oh, that's not crazy. 10 nanoseconds. Yeah, it's not bad. How do they do that though? Okay, this is some of the mutant expert crystallography, yada yada yada. Represents snapshots of the enzyme on the pathway, with residues interacting. In the figure, the ATP lead is shown in the blue cartoon, the AMP is the gold cartoon. Okay. A, B, C, D, E. That's neat. Snapshots of the enzyme and substrates in two different states. A, B, what the, wow. That's cool. I got 0 views. I think most of my audience is employed, so that's kind of nice. Yeah, so this is super fascinating because like if this ends up working well, like you could essentially like get these subtle like differences between what makes the ligand bind and unbind. You know, that's very informative for like mutational studies, and it really kind of supports the idea that they're getting like a very detailed MD picture. You know, phases were but it looks I don't it looks kind of hard to do. I don't know. Okay. So this is all like X-ray stuff. For energy profiles of hollow enzyme opening, discover that AK has a higher tendency for opening in the product state, where it is bound to two molecules of ADP. Consistent with this tendency, the product state exhibited a notably diminished free energy barrier for opening in comparison to the product exhibited a notably diminished free energy barrier for opening in comparison to the reactant state. Oh, okay. Okay, I see. Diminished free energy barrier for opening. Yeah, that means it's more likely to open. All right. Furthermore, we established a mechanistic linkage between the catalytic phosphor transfer and the enzyme's opening dynamics proposed based on the findings. Okay. So the mechanism to accomplish this, we conducted free energy enzyme opening while concurrently releasing zero. So this is going towards the product state. Right? Isn't that what that means? Starting from the reactant state, the system was progressively mutated to the product state. Okay, what is the reactant state again? That's just the reactant state. Okay. So the product state is 1 here, right? Oh no, that's lambda. What does this alpha mean? Get my wires crossed. Establish a mechanistic linkage. And finding that both modulated by the active site residues take on a similar timescale. To accomplish this, we conducted. Yeah. Okay. So this is the X-ray crystal structure. The resulting free energy profiles are presented in Figure 2a, where okay, alpha represents the normalized coordinate reaction coordinate describing both ATP, AMP lid motions, and ligand release. What are we talking about? Figure 2a. Figure 3 provides snapshots of the bound ligands and their interactions at different alphas for reactant state. Analogous snapshots for product state are presented in Figure S2. So alpha represents the normalized reaction coordinate. Which I don't really know how they computed that. Free energy profiles exhibit distinct patterns along various stages of the opening process and also between their actives. Specifically, we observe the free energy profile between alpha is predominantly influenced by the opening of the enzyme, while it is dominated by the release of the ligands. 0 to 3. Yeah, so this is opening, and this is the release. Cool. In addition, during the opening step, the free energy barrier for opening in PS is notably lower. With the value of that, this difference can be linked. These findings are consistent, which will determine the presence of ligands, but without incorporating their motions into CVs. That's kind of what we're doing right now. Detailed sequence of events. Shows the stability, close conformations via anchoring, thus the loss. So helix A7. So that's what it's talking about here, right? A7 and A4 increase in distance. That's cool. This contact, yeah, thus the loss of the contact. That's a slight displacement, which also observed in a previous study. Subsequent arginine 156 lifts upward. It's a key residue in the catalytic loop of the enzyme, which is located right above. So arginine 156 lifts upward. Moreover, this residue forms stacking interactions in the close conformation. Any mutation thereof would show substantially reduced catalytic activity. Therefore, breaks the stacking interaction. Interestingly, it occurs at different alpha values between the reactant and product state. Okay. In the product state and despite this difference, this event seems to occur immediately prior to the transition of opening and breakage, stack, are critical first events for the opening of the enzyme. Therefore, it makes sense to observe the facilitated opening of the enzyme via any mutation that breaks on the other side of the enzyme. Adenine base is released from the binding pocket formed ATP recognition loop. What makes up an ATP recognition loop? Like, can you predict that? Glycine-rich sequence, followed by conserved lysine and serine threonine. So I have some sequence similarity stuff that I need to go through. It'll probably be tomorrow or something. I have a lot of stuff I'm looking forward to trying actually. These changes allow the upward. Recently we observed the replacement. This can be a length. Okay. Observed that the replacement stimulated opening of the enzyme. This could be linked to the fact that bidentate hydrogen bonding interaction. Yada yada yada. Okay. Cool. Around 0.3, the ATP is almost fully open. This difference of opening. Slight loosening of the AMP lid was observed before the full ATP lid. This is incredibly detailed. The during. Which is good. In RS, the ATP also interacts with that. Even at this point, however, the ligand remains bound, including the deeply bound base. Where another catalytic residue interacts with in the release. Okay, for energy contributions. Continues to rise where ATP lid remains open. Therefore, this change in free energy is mainly due to the release of ligands, particularly in contrast to free energy released before is primarily contributed. Opening the lid. To gain further insights, we decompose the SMC free energy profiles into contributions to the protein. Notice that the increase in free energy is indeed dominated by ATP lid, the free energy. How do you do that? Can you just calculate this? Oh, I guess you can. Yeah, this is something I gotta look into. Man, I just wish I had more time, man. In contrast, the contributions of the ligands is relatively small. This increase is both a significant contribution. Ligand's contribution is notable for PS. Okay. The first step. AMP lid opens with a relatively minor energetic contribution. Okay. Did they add a free phosphate in there? which is estimated. Specifically, we obtained as calculated. I want to talk to these guys. Particular significant errors occur in both enzyme opening and ligand release, which is likely a result of large fluctuations. The KD value. What does KD mean again? That's really bad to ask, but dissociation constant. Low KD, high affinity, high KD, low affinity. It's just the ratio between off and on. So what would be considered like a high KD? Right? Overestimated the free energy. Free energy of ligand release. Directly computing the free energy of ligand release using methods may not be straightforward due to conformational changes in protein. Nevertheless, our simulations show ATP requires more energy to be released compared to AMP, which is consistent with the smaller KD value. Was it on over off? Oh, off over on. So the higher KD, the lower, the lower the affinity. So ATP has a higher affinity than AMP, because AMP has a ATP has a higher KD. No, a lower KD, right? Yeah. Right. Likewise, the release of ADP how long did this take? First, it's clear to show that early currents. Figure 7, we superimpose the average structures. Oh, okay. Coordinates are shown to be equally as a mimic of the catalog. There's gonna be a lot to talk about. I don't have to go into too much detail about the specific residues that contribute to opening and stuff like that, like they did. Really, just want to like talk about the technique they used. It's kind of the core goal. The study also found that even in the closed state, the study also found that the AMP lid remained open even in the closed state. Notably, yeah, inspection of the. All right. Uh, okay, fair enough. So the present study distinction is achieved by comparing the free energy profile associated with the enzyme, determined as a function of between close. The results indicate an induced mechanism primarily goes to early stages of finding. Um, Cooperate. It is worth noting that alternate pathways are also possible. For example, ligand binding may first induce the closing, this closing. Okay. The charm parameter topologies input sample instance and system files. Ooh. Can be obtained upon request. Okay. Um, cool. My guy is sick. The pre-presentation got you. No, I'm not. This is a very low stress presentation, to be honest. So, there was actually like the previous, like I was supposed to present. I'm actually supposed to present this Monday, but last Monday the meeting was skipped. So I'm kind of doing a joint presentation with the guy that missed last Monday. So my time's gonna be cut in half. So um, I have a bit of an excuse to not be as thorough. All right, but I just finished the paper, so I'm gonna start diving into like the details more now. Um, so I like asking. So like here is a paper. You are scientific reviewer. Summarize the paper and give your opinion. So ChatGPT usually like shreds these papers. I don't know why they just don't give us the data then. Like they could create a. Oh, never mind. MD inputs and topology parameter files. Come on. Oops, I didn't mean to close that. Do they give it to us? For once? Oh my god. There we go. Why is it a music file? What's this say? Structure and information to run the empty below the end run counter should increase by 1 for each run. Thus, GPU must be available. Export open device. Okay. This is great. What's this? Am I gonna have to learn Charm? Alright, let's do this. Ooh. So let's see. Oh, so did they parameterize? Oh, wait, no, they didn't. What are these guys? SOD? Nice. So now I know that I can mimic the protonation states here, which is good. Like, what is that? ADP. So this is just regular ADP, and this is ADPP, which is, huh? What is that? I don't know what a PSF file is. Oh, there we go. This looks. So this is ADP. This is ADP again. So this is the product state. Wild type RS. Okay. So yeah, this is ADP, this is AMP. Okay. SVN input for hollow system. Yeah, let's get that too. This looks like a big folder. Empty. It's empty. Okay. This provides the instructions less information to run SMCV. Below NV type can be opt for the path optimization. Job. MPI run. Is Charm open source? Oh, nice. So I can do like conda install Charm. Oh, it's OpenMM. Okay, so they just use OpenMM for this? MD script. Okay. I don't know what that means. Don't know what that means. Let's see what ChatGPT said. Authors use a string method and collective variables with animistic MD to find or to map for energy profiles. They decompose the PMFs into protein ID or lid opening and ligand release. Contributions. This is all X-ray crystal. Okay. Minor to moderate revisions. It's actually pretty good because ChatGPT usually is pretty mean. Okay, so three-step release pathway in the hollow enzyme. Let me change this music. I got a song rec. Okay. Three-step release pathway in the hollow. ATP lid opens. All phosphate remain P-loop bound. AMP lid then opens and both ligands exit binding pockets, nonspecific surface positions before full dissociation. Mechanistic split and binding. AMP lid closes by induced fit, whereas ATP lid closes by conformational selection. Early kinetic trigger, lifting, okay. State dependence, opening barrier is lower in the product state than in the reactant state. APO opening proceeds with AMP lid opening first. Calculated delta G matches KD expectations. So our estimate attributed to large fluctuations when ligands form nonspecific contacts. Multi-microsecond SMCV with explicit and separate CVs for lids and ligands. Clear qualitative picture. path initialization bias. The PS release path is generated by steered pulling, and the RS string is derived by ligand swap plus short equilibration. This can imprint hysteresis. I don't know what that means. I think actually that's a good word actually. So when you substitute the ligands, it's gonna have some hysteresis, meaning like lag time to catch up to what it's supposed to be at. And that's kind of COM distance CVs, Mimas rotation shears, center of mass, local cracking of insert. For energy decomposition is not neat. Partitioning PMF into protein versus ligand contributions depends on the CV set and coupling. Contributes little for energy, should be tempered. Converge with largest discrepancies. Okay. So what do I need to do? Okay, let's so first probably here I want to define like the methods basically. Okay, let's go over the details of the methods they used. What software was it? How many nanoseconds did they simulate this for? What force fields did they use? What is SMCV? Is that what it's called? Yeah, SMCV. How do you calculate the reaction coordinate? And then we should probably try to find a figure. I mean, this seems like a good figure to start with. I don't know. Hollow means bound, right? Yeah. All right. Charm, program, DOM, deck, GPU, and OpenMM. What is Charm DOM deck? It's just for GPU acceleration. That's cool though. Alright. Generated an generated an opening trajectory and product state used to seed strings. All string method. String method. What is string method? It's a computable technique used to find the minimum free energy path between different states of a system, reactant product states in the chemical reaction. This method operates within reduced dimensional space. Define a set of chosen. Oh. I disregarded this last time. But it's finite temperature string method and collective variables. Do they use Strom here? Whoa. Okay. Hollow reactant product. Path represented by 64 images. Path optimization per image. Reactant state 20 nanoseconds, product state 28 nanoseconds. 60, 100. So that's like five microseconds is like 5,000 nanoseconds. Yeah. So that's a lot of time. What is SVM? String. You discretize a reaction tube by images in a reduced CV space. Here, lid, core distances, and ligand lid distances. You harmonically restrain each image in CV, run short MD, accumulate mean forces on the CVs. Evolve the string along the free energy gradient, reparameterize, and keep equal arc length between images. After convergence, you run longer restrained MD at the fixed to get an integrated PMF. Oh my god. Alright, so let's do this. So delete that. Insert new slide. So we'll do methods. we'll trim this a little bit. MD images, charm, open MM. I'll just say that. Okay. How long did they simulate? That's kind of a hard question. Okay, so did they basically run normal MD to get the opening and closing, and then they did SMCV, or did they use SMCV to get opening and closing in the first place? Let's start with the hollow case. Okay. SVM did the heavy lifting. Plain MD was used only to seed the path and then do quick calibration, not to map the whole opening closing free energy landscape. Hollow case. So product state, they ran unbiased 2 microsecond MD. The enzyme opened spontaneously at 1 microsecond. Ligand still interacting. They did a brief steered MD segment to move the ligands outward and stitch together a continuous opening plus release as an initial gas. From the initial path, they ran SMCV to optimize the path and then compute. Nice. Okay, that makes sense. So this is the product state. Reaction state. Unbiased MD, the same length, did not open. So they reused the product state path, swap ligands to ATP, AMP, equilibrated 1 nanosecond, then ran to optimize. No. Normal MD only provided the seeds and sanity checks, the opening, loose pathways. Okay. So we'll do new slide. ATP plus AMP is the reactant state, 2-ADP is the product state. They ran unbiased 2 microsecond MD. The enzyme opened spontaneously at 1 microsecond. Ligands still interacting. They did a brief steered MD segment, pulling equilibration to move the ligands outward and stitch together a continuous opening plus trajectory from the initial path they ran. To optimize the path, then compute fringe path coordinate alpha. Okay. All right. Um, okay. Okay, and for steering, they basically used the COM of ligands and the lids to drag them apart. How long did it take after the SMCV to get the full opening path? Did I change the title of this? Oops. Is that right now? Oh, I am live. Okay, sweet. All right. They did almost 2 clarifications for the hook. They steered to make the seed path. What is a seed path? They did a 2 microsecond unbiased product state, aka opened 1 microsecond in. They then pulled the ligands outward using distance constraints on each ligand center of mass from its binding pocket, not directly from the lids. That stitch trajectory was an initial guess of the reactant state. Path optimization, making the path itself. Reactant state, 20 nanoseconds per image, 64 images. 28 nanoseconds. PMF accumulation. Hmm. How long did SMCV took to produce the full opening path? What does man image here mean really? Is this a checkpoint to get to? Within X amount of time? PMF accumulation. What does PMF stand for? Potential of mean force along the path. Free energy profile along that path. What how did they optimize PMF? Is this the force of the CV? Is this the force of the bias potential? Hmm. This paper seems like what you would need to do, like the bare minimum requirement for like biased MD with a collective variable. Where are these people from? Texas? What's this? Can only reach. Oh boy. What is an image? Think of a reaction path as a bead along a string, but in CV space, not real space or time. Each image, one bead, a target point, and a chosen collective variable. Here the vector of COM distances for ligands. Images do not represent time checkpoints. You must reach after X nanoseconds. They're waypoints that define the shape of the path in CV space and around which you do short restraint MD to sample local mean forces. Okay. There's no schedule to hit. During optimization, you hold the system near the image with a harmonic restraint on the CV's sample, and then move the image, not the clock, using the estimated free energy gradient. After each update, you reparameterize the string so the image stays evenly spaced by arc length. Okay, that makes sense. So I should probably insert like a SMCV molecular dynamics. Do they have like a good representation of this? String method. There we go. With swarms of trajectories. This would be a good figure, I think, to drop in. What was that? Alright, what the hell? I want this one. I didn't mean to do that. Oh no, I need to save it as a PNG, I think. Maybe not. That's fine. String method. String method and collective variables. All right. Think of the reaction path as a bead on strings, but in CV space. Each image, one bead, a target point in a chosen collective variable. Images do not represent. Not exactly. So the path optimization use short restrained MD at each image to estimate the free energy gradient in CV space, update image positions along the downhill direction, then reparameterize, repeat until the path geometry converges. Use short restrained MD at each image to estimate the free energy gradient in CV space, update image positions along the downhill direction, and then reparameterize. Repeat until path geometry converges. PMF evaluation. With a converged fixed path, run longer restrained MD at each image to estimate dF over dA and integrate along the normalized path coordinate to get PMF. So how do they know? How do they know what the downhill direction is? Okay, no. Like, how do you converge a fixed path? Using the estimated free energy gradient. How do you do this? Would this not have been possible if they did not see the opening of was it product state in the unbiased MD? No, the harmonic is just sampling device to keep the system near the images to see the quantity they need is the mean force of the physical free energy in CV space projected onto the path tangent. Oh, okay. In practice, under harmonic restraint, the time average restoring force provides an estimator of the mean force in the CVs near that image. They then project that mean force vector onto the path tangent, finally to integrate to 0 to get. So you use the bias to estimate. You do not report the bias force itself. Let x be the atomic coordinates and that the vector of chosen CVs here. So you have distance lid to core, ligand to lid. At image I, string stores the target CV point Z. Restrain MD at image I. For sufficiently stiff K, the average spring displacement gives a negative gradient of the physical free energy F at Z. God. String update path optimization. Compute the unit tangent to the current discrete path at image I. Move the image downhill orthogonal to the path. Then reparameterize the whole set of z to equal the arc length spacing. What? I do not understand that. Compute the unit tangent to the current discrete path at image I. Move the image downhill orthogonal to the path. I don't get that part at all. Okay. Um, For sufficiently stiff K, the average spring displacement gives negative gradient of physical free energy. What is physical free energy? So we are sampling around the images and finding one that has a lower free energy. Oh. Compute the unit tangent to the current discrete path at image I. Move the image downhill orthogonal to the path. What do you mean by move the image downhill? Downhill to what? Why is it orthogonal? What is arc length spacing? Can you use dummy numbers, please, and speak in a language that is simple? Do not simplify. trapezoid rule? Like, what the hell is that? Is there like a YouTube video on this? This one, maybe.
Greetings.
Okay.
In this video, I want to tell you about a method to find optimal paths between different states. It's useful in a variety of physical systems or situations, but of course I'm going to frame it in the context of polymer physics. If you've seen other videos on this channel, you probably know that polymers can form a variety of stable or metastable structures, but it's often useful to understand how one structure can turn into another. This can happen through some kind of instability, like spinodal.
So last video the volume's really loud, so I'm going to turn it down a little bit. It's too quiet then.
Where the initial
Sorry.
state becomes unstable and gives way to the final state, as shown here. On the other hand, it could happen that the initial state is metastable, like this modulated disordered phase that's just hanging around for a while until a droplet of the lamellar phase happens to randomly appear and happens to be large enough to grow. You can see it starting to appear at the top of the simulation box, and now it's growing to engulf the system. We can picture this in terms of the free energy landscape, here shown as a function of some abstract reaction coordinate. It fluctuates around this local minimum for a while until the fluctuation is large enough, then it goes over this hump and falls down into the deeper free energy minimum. A simple description of this is available from classical nucleation theory. Consider a droplet of the lamellar phase in a bulk of the disordered phase. The disordered phase has some free energy density, Fd, similarly for the lamellar phase, Fl, and thus some difference sigma. Sigma acts like a pressure. If it's positive, the system lowers its free energy by converting disorder into lamellar and growing the droplet. There's also a surface tension, gamma. There's some structure to the interface between the lamellar phase and the disordered phase. We can immediately see that the free energy of the structure has to be larger than either of the phases. If it wasn't, well, the system would prefer to be in that state rather than either of the metastable states, so this would be the metastable structure. So the surface has to be unfavorable and gamma is positive. We can therefore write the free energy as a sum of the surface term that varies with the length of the droplet squared, and a volume term that varies with the length scale cubed. For a spherical droplet, these terms are proportional to the usual surface area and volume of the sphere. The droplet that we just saw was clearly not spherical. This is due to a dependence of the surface tension on the angle at which the lamellar phase meets the disordered phase. A full description of this is beyond the scope of this video, but if you're curious, I recommend looking at the Wolf construction. If we plot this free energy, we get a shape like this. There's an initial increase due to the positive r squared term, so the droplet can lower its free energy by shrinking. This is followed by a decrease in the free energy at large r, so the droplet grows. In between, there's some critical size for the droplet, and this gives the barrier to the nucleation. A similar description applies to the nucleation of a pore from a membrane at fixed tension. This time, we have a line tension around the pore, and a membrane tension acting like a pressure pulling.
I don't know if this is
of course, real life is
relevant
rarely
to
so
what I'm
simple.
doing.
For one thing, classical nucleation theory works well when droplets are large. So let's go back to our free energy sketch. I'll make up an order parameter and call it alpha, and I'll label the beginning state alpha equals 0, and the end state as alpha equals 1. And we can try to come up with some parameterization that takes our system through the intermediate alpha values. We can describe the state of the system in terms of the density rho. Let's assume that the system is incompressible. This allows us to use the concentration of just one monomer type for simplicity, but there are obvious ways to generalize this. I want to emphasize that we can think of this function as a vector in some Hilbert space of configurations. Every point in real space corresponds to a dimension in this Hilbert space, and the projection of the location onto this dimension is the concentration at this point. If you prefer, you can think of the state of the system as a set of row values at every point in space, and we can put that set of row values into some big list, the column vector. In practice, we discretize rho onto some kind of grid, so rather than an infinite dimensional vector, we have some finite dimensional vector. Still a lot, though. We might want 100 points in each direction for the system. This leads to 100 cube points, i.e. our state is a vector with a million dimensions. Changing the structure is the same as changing the vector in our configuration space, or changing the point in Hilbert space.
Alright. That's too much, I think. Alright. What is the physical free energy here? We compress the full atomic system X into a few collective variables, e.g. Okay. Core ATP lit distance, core AMP distance. The physical free energy, aka potential of the mean force PMF in that CV space is that. And formally, at CV value Z, many microstates X are thermally accessible. Oh, how many microstates? More microstates equals larger integral Lower F. This F is a property of unbiased system, the real Hamiltonian, not any artifact restraint. What is an image and what do we do with it? An image is just a waypoint Z in CV space. A string is a chain of these points from closed to open. At each image I, we run a short restrained MD with a harmonic spring in CV space. The spring keeps sampling near Z, so we estimate the mean force of the physical free energy there. Key estimator, intuitive. If the spring center Z sits uphill in F, this is how you calculate F over here. More microstates. Microstates X. What is a microstate? The spring center Z sits uphill in F, trajectories will on average be pulled downhill. So the spring stretches towards F. That average stretch tells you the negative gradient of the true free energy, tiny numbers. Let CVs be in nanometers. The image we set, see it's boom, boom. Spring constant, sure. From a short restrained MD, the average CV we actually sample is that. Average displacement's there, estimated gradient. Oh, interpretation. Increasing Z1, or yeah, raises F quickly, negative gradient. Increasing Z2 lowers F, increasing. Downhill means the direction that decreases F, but we don't want to slide images along the current path. That just relabels them. We want to fix the path shape so we only use the components that is orthogonal to the local path tangent. That's what orthogonal means here. Y. Tangential component changes where we are on the path, not the path's shape. Normal orthogonal component actually bends the path towards tiny numbers continued. Suppose the unit tangent to the image, gradient from above. That's what that is right there. Project gradient onto tangent. Normal component. Take the small step downhill orthogonal to the path. What's the arc-length spacing and Y reparameterized? After updating all the images, some may bunch up while others spread out. We want to normalize path coordinate to advance uniformity from one end to the other. That's what equal arc length means. Geometric, okay. So compute cumulative distance along the polyline. Resample the polyline so images lie at evenly spaced tiny numbers. No, there's no accept, reject, or pick the lowest logic. At each image, we estimate the gradient of the physical free energy using the restrained MD, then deterministically nudge the image downhill, orthogonal to the path, iterate. Okay, I think I'm getting it a little more now. I don't know why more microstates lead to a larger integral. Hmm. A string is a chain of points supposed to open. At each image object run is short. So what if the spring center Z sits uphill? Is it always uphill? How many microstates are thermally accessible? Is this like how many? Are you saying how many conformations are there that um, uh, that satisfy the CV? F is the property of an unbiased system. Potential mean force PV in that CV space. So we estimate the mean force of the physical. So at each image we do this. And then if the spring center Z sits uphill, trajectories on average will be pulled downhill, so the spring stretches toward. That average stretch tells you the negative gradient. Oh boy. Estimate gradient. This is equivalent to this, which equals, so interpretation, increasing Z1. What do you mean by increasing Z1? is this saying we select the frame where core ATP lid distance increases? Downhill means in the direction that decreases F. So let's change this then. But we do not want to slide images along the current path. That just relabels them. We want to fix the path shape so we only use the components of negative f that is orthogonal to the local path tangent. That's what orthogonal means here. Why? Changes where we are on the path, not the path shape. Normal actually bends the path towards valley in F. This is the shape we seek. Tiny numbers continued. So I'm envisioning like a curve. There's a tangent line, and then the normal would be like a line that like makes a cross with the tangent. So we take a step along that path. How do we take a step in the normal direction? What does, practically speaking, I kind of get this though. I wonder if they can make some figures for me. When we are defining the path, are we essentially calculating which frames that we simulated are orthogonal to the tangent of the gradient? We aren't actually steering it per se. Oh, it's complicated. doesn't rain while I'm walking. So what would be the, so I'm right here, essentially. Free physical energy in CV space. If you choose a few collective variables, the physical free energy tells you how favorable it is for the real unbiased system to be at those CV values. Okay, intuition, it's temperature weighted. How many microscopic conformations have those CVs? More ways, lower F. In practice, you don't enumerate conformations. You sample near the target with harmonic restraints in the CV space, then estimate the gradient where they're from averages. Okay. Increasing Z2, what does that mean? It means change the CV value by a small amount and ask, does F go up or down? It doesn't mean pick a particular trajectory frame. You are reasoning about the CV coordinate, not selecting an MD snapshot. Okay. We are selecting the frame where core, no, at a given image I, you center the spring, run a short restraint, and collect how many frames that fluctuate around Z. The average displacement of those fluctuations tell you the direction of lower F details. Okay. How do you move an image downhill? Downhill to what? Downhill, lower F in the direction. Yeah, but you change the shape of the path, not just its labeling. You only keep the part of orthogonal to the current path tangent. The tangent part just slides along the path. The normal part actually beads the path into valleys of F. Average displacement, estimate the gradient, local tangent, project the gradient into normal directions. Okay, take a small normal downhill step. New image. That's all done in CV space. After moving all images like this, you respace them, then repeat. Okay, I think I'm getting it. Take the normal. Y orthogonal normal updates change the geometry of the path. Tangential updates just reparameterize it. Okay, are we calculating which frames are orthogonal? No, orthogonality is about vectors. Not about classifying frames. Frames from restrained MD are only used to estimate. Okay, images are what get moved. You're not steering along the path. You're doing many short local restrained MD runs and then moving the image centers. Oh, okay. I see. Okay, so are we essentially relabeling the okay, what? You're not steering the path. You're doing many short. So that's the key thing right here. It's iterative local sampling plus geometric updates in CV space. Conceptually reflects how many Boltzmann weighted. Practically, you don't count them. You sample near Z with a restraint, measure the average, and then turn that into and update the images. We're essentially relabeling the images based on the free energy estimation so the path will be a list of distances that increase or decrease over time to get to the end. Is that right? Moving the image centers in CV space. So what's this stuff? I think I'm close. That's kind of cool though, that updates the geometry of the path. Tangential updates reparameterize it. You move and lightly relabel images. You're not sorting by energy. You're adjusting their positions in CV space using the free energy gradient and reparameterize a mild relabel so that they stay evenly spaced along the path. What changes each iteration? Move, update images. Each image is physically moved in CV space a small step downhill orthogonal to the path, meaning using the mean force estimate, reparameterize label. After the image moves, you respace them to have equal arc. So is the path a list of distances that increase to the end? No. The path is a list of CV vectors along any individual distance can go up to be non-monotonic. Only alpha itself increases. The coordinates don't have to. kind of get it. I need to hurry up and get it, that's for sure. You do two things each iteration. Move each image's coordinates in CV space using the estimated free energy gradient as the shape of the path. Relabel them via reparameterization. So it's along the same polyline. So yes, there is a relabeling step, but it's secondary. The essential step is that the images are physically moved in CV space toward lower free energy, not just retagged. The path parameter alpha runs by. Some rise, others stay flat, some fall, whatever the optimized path demands. Here Z1 grows early, and it changes, and it's along the alpha. Okay. Now I'm picking single frames. You're updating CV targets using mean forces estimated from many frames near each image. Okay. So after each update, we are asked to simulate around the CV. So we pick the frame whose and then run it to get I mean, I know we're not picking frames, but like, is it just we do this one time and then, um, like, I just don't get it. You don't pick a single frame. After each update, image centers a CV. You run a short restraint around each image's target CVs. You move the images again. Okay, hold on. I'm just right while restrained. For picostep per iteration for path optimization start configuration. Typically the last frame of the previous restrained run in the same image. You're already near Z. In this first iteration, you seed each image with a configuration taken from the initial guess geometry near that CV. Oh, okay. For each S image, for the path was then evolved with free energy gradients followed by reparameterization to have equal distant to converge as they froze the images to compute PMF along alpha. Okay. I'm kind of, I think I'm getting it more. After converges, compute PMF, not with the string fix, you run longer at each image to reestimate, numerically iterate. You're not computing the free energy of a single CV point isolation. You're computing to make it tangible. So we have 3 images and 2 CVs. So this one, so these are all images. Okay. Alright, I think I'm gonna pause here. I need to get back to the stuff. So maybe I'll stream later tonight. I don't know.